The New Quantum Era,
a podcast
by Sebastian Hassinger
and Kevin Roney.
Welcome back to another episode of the podcast. This is the third episode that I recorded when I was at Rensselaer Polytechnic Institute in Troy, New York. And in this episode, we had a conversation with Jamie Garcia from IBM Research. She is the Technical Program Director for Algorithms and Scientific Partnerships and a quantum chemist by background and training. So it's a really interesting conversation. It's another in our series of investigating sort of the near-term applications for quantum computing, where there's an expectation that chemistry in particular is one of the areas where there will be applications that have significant value and a quantum advantage in the near future. And Jamie talks about the exploration that IBM is doing right now with a lot of its research partners into what they call quantum utility, which is really the frontiers of what you can do scientifically with quantum computing, simulations, small-scale chemistry, ground state calculations, and some dynamics simulations as well. It's really interesting. We also talk about the fact that the Rensselaer community now has an IBM System 1 on premises in their data center, and what that may mean for the research and educational opportunities to the RPI community. So that's really interesting. And I want to thank again RPI for providing this great podcast recording studio and for giving me the opportunity to talk to all these amazing people during the launch event. It was really enjoyable, and I think you'll enjoy this conversation with Jamie as well. Joined today by a special guest, someone I've worked with before at IBM, somebody who's still at IBM Research, Jamie Garcia. Welcome, Jamie. Thanks for joining.
Thank you, Sebastian, for having me.
Very happy to have you here. We're at RPI. We're at the launch event for the IBM Quantum computer that's being deployed on campus, first on any university campus in the world. Which is super exciting.
So exciting,
yeah.
Yes.
And you actually had a huge hand in organizing the entire event, so congratulations.
Oh,
it's
thank
going
you.
Great.
I've been so excited to see how it's been going, truly.
Yeah, it's been terrific so far. We're about halfway through, and I'm super excited to see the ribbon cutting tomorrow. So why don't we start just with the basics? If you want to just introduce yourself really quickly and a little bit about how you got to where you are in quantum.
Sure. Yeah. So I'm Jamie Garcia. I am the Technical Program Director for Algorithms and Scientific Partnerships group with IBM Quantum. My background is in chemistry, so I hold a PhD in chemistry where I focused a lot on catalysis. And then now I've been working in quantum computing for about 8 years, which is crazy.
You're
how
a
time
veteran.
flies. I know. It's crazy. I felt like such a newbie in the beginning. But yeah, I basically through my chemistry research worked with a lot of computational scientists as a part of that journey. And there were a couple moments during research that we were trying to look at a mechanism for something or understand the theory behind what we were observing in the lab. And we couldn't explain it at all. And then when we turned to the computational chemists, we had to use a lot of approximations, right, to be able to understand the systems. So I think a little bit of my journey into quantum was based off of that experience, because I recognized at that point that there was some severe computational limitations, as advanced and as the science is, don't get me wrong, that needed to be addressed. So the first time I saw a quantum poster on chemistry being presented in Yorktown Heights lab, it was Abanov's paper in 2017. And that just I was like, oh my gosh, this is a new tool.
Right.
Like, we've
right.
got to try this
Yeah.
and just see how it goes.
Yeah. So you were with IBM Research already, but as a computational chemist or in that kind of...
I come from an experimental background,
Okay.
actually. So, but worked very closely with computational scientists because oftentimes we would make an observation in the lab
Right.
and we couldn't explain it, or we needed to know how to control what we were doing.
Right.
So
always good to do.
always good to do, right? Maybe not have the, explode that day. Anyway, so we leveraged it a lot. And I think, a lot of times these processes, it would take months, years
right.
of back and forth
Right.
between lab and, talking to the theorists
Right.
to try to figure that out and then get it to a point where you actually could control it. So anyway, that's my background.
Cool. And that actually gives some framing for that article you wrote in Scientific American. I think it was 2019 or 2020, something like that.
Yeah.
I really like that because it put it sort of framed quantum computing as a tool to bridge that theory
For
to
sure.
experimentalist kind of
Yeah.
space in chemistry, right?
Yeah, I think for chemistry and materials and the way that we leverage computation, that's sort of the holy grail is reducing the amount of time that it takes for that iterative process. So from, I just said months or years, sometimes it can be even longer, right? Especially if you're looking at industrial processes where
Right.
it has to be so precise.
Right.
If you can reduce that down to really as small as possible, and even, the vision of it being in a someday world that you would have calculations that were so accurate that you don't even need to go into the
Right.
lab first.
Right.
You can do it in silico. You can
Right.
do it on a computer.
Amazing.
And you know that the answer is going to be if not perfect, pretty close.
Right.
And so then that just kind of flips the way that we do chemistry on its head.
Yeah.
So yeah, that's the idea. The other thing that I think is really important to recognize about the impact on chemistry too is that you have new opportunities, right? We talk about utility to actually leverage, and this is the first time I've actually thought about it this way, the quantum computer as the experiment. So in other words, you do the theoretical, tensor network calculations or whatever, and then run something on the quantum computer, and that's your experimental validation of the theory. So that's a new paradigm.
Right.
And I think that can be extended out, beyond condensed matter at some point, right?
Right.
We expect it to be applicable and to see utility
Right.
style experiments and examples for
Right.
chemistry materials.
And before, I want to get to where you're going right now, but I want to just loop back for a second.
Yeah.
I think people don't really understand, computational chemistry, classically done, you said approximations. It leans really heavily on approximations. A lot of data is just thrown out so you can get an answer, right? And you're trying to guess essentially what data you can do without in your computation and still get a usable result. Is that sort of right?
It's what you can kind of get away with, right?
Yeah.
So anything. So Schrodinger's equation, anything beyond H2, you cannot exactly simulate.
Right.
You have to invoke approximations.
Right.
It gets too complex. And so that, I think, in and of itself is a really good driver for a lot of the, thinking about how you could potentially use quantum to approach some of these similar problems for ground state energies, excited state energies, properties, and things of that nature. But yeah, if you look at something like density functional theory, which is, again, probably one of the most heavily utilized, methods in computational chemistry. That evokes approximations where you essentially are having to set up your electron in sort of a electronic field that you have sort of as a fuzzy approximation for it. And it works Pretty well. But again, I mean, it really does lend itself to the type of process that I was mentioning earlier, where it's a lot of back and forth,
Right.
a lot of experimental
Right.
validation in the flask, not
Yeah.
on the quantum computer yet,
Yeah.
to be able to proof these out. And a lot of times the first answer you get is just so very far off.
Right.
Yeah.
Right. Okay, so getting back to, you use the word utility. It's a word that IBM Quantum sort of adopted in the last year or so, because I guess you guys feel like the machines that you're producing and the algorithms are right at the edge of sort of doing things that are not classically possible, right? So you're starting to, in a way, it feels like it's starting to fulfill that promise of that Feynman made it in Endicott of, like, if you want to simulate a quantum system, you need a quantum device. And so you're starting to do quantum or simulate quantum systems that are not easily simulatable classically. Is that accurate?
Yeah. So I think, even in the case of the actual paper, right, like some of the response by the field was immediately to, publish their own papers on the classical, methods, right? And I think that something that was really interesting in that is, and maybe you've seen this plot, but if you like overlay it with, what we got on the quantum experiments, the actual classical methods deviate by around 20% from each other. And it's because they're great methods. They're very sophisticated.
Right.
But at the end of the day, there's still some sort of approximation that you have to evoke.
Right.
And so that is, I think, what we're really thinking about and starting to expand. Okay, so if you go beyond the icing model, what are the other things that you could potentially look at
Right.
that have a similar construct? And it's always going to be like the classical fields, and classical approaches are always going to be advancing at the same time, right? And so I think there's a lot to be learned just by doing the experiment.
Right.
Like the fields can learn from each other.
The first the experiment that you guys used as an example, the sort of use of the utility word, was where I learned the phrase "kicked icing model."
Yeah.
I love that. I love that turn of phrase. It's hilarious.
Yep.
But yeah, so this sort of you're on the verge of sort of doing things that are not classically easy, or the classical, as you said, the classical result has variations, they're approximations, and you're getting something that's higher fidelity essentially with the simulation. So coming back to chemistry, do you think, like, are we at the point where we're going to start seeing this as a practical tool in the computational chemist, the experimental chemist sort of dialogue back and forth?
Yeah, I mean, certainly I do. I think it's going to be a challenge to think about different examples that are going to be sort of the utility example, if you will, for chemistry. A lot of the problems are really large. So chemistry, one of the biggest challenges with it, when you start looking at the quantum circuits necessary for it, is that there's a really large depth requirement.
Right.
And so, you could have like a 5-qubit example and a depth of, easily like 5 to 10x that number.
Right.
And so having to figure out what to do with that, I think that's where things like circuit knitting, circuit cutting comes in.
And error mitigation potentially, right?
Yes. Error mitigation, like we use systematically, basically, in any of these examples.
Right.
So it's going to be a combination probably of the techniques, and it's dependent on the problem. But yes, I do foresee that it's going to start becoming a tool. I mean, the most interesting innovations, I think, are what comes out of when you actually start looking at the hardware for things and trying things out.
Right.
Really understanding what error mitigation needs to be used. We've seen for different problems that you need different. You need to tweak the algorithm, but you also need to like change which error mitigation methods you need to use for that.
Yeah, I was going to say, we interviewed Martin Savage from University of Washington just a few weeks ago, and he told us about the experiment he did over Christmas, basically.
Yeah.
And the nature of his problem allowed him to do some pretty impressive error mitigation that got I think his depth was something like 15,000 gates or something. It was it was a lot.
Yeah.
With 102 qubits or something involved.
Right.
It's like really impressive.
Right. Yeah. And I think, so all of those methods are going to be really, again, and I think also too, another important piece here is that your intuition goes a long way. And so the people who are able to get like the best results on quantum hardware are folks that have been, trying their hand at it for a while. And they get an intuition of like, okay, if I'm going to look at this type of problem, these are the kinds of things that I need to do. And so your starting point is a little bit closer.
Yeah. Yeah. And I think Martin has been working on IBM systems for quite a long time. I was surprised how long he's been doing it. So, it's a very good argument for industrial R&D scientists to get involved in this stuff as early as possible because,
for sure. And you talk, we've talked a lot about the sort of continuum, if you will. And like one of the things that I think is was a point that stuck with me when we were talking about our roadmap that we put out at the summit is that there's not going to be a fundamental difference in the API between like the error mitigation devices available in the next 4 years to then when we switch over to now being in a regime where we have access to logical qubits. And so in principle, if you're learning now, you're not going to necessarily notice the change because it's just what's going on under the hood that's changing. So even more impetus, I think, to start as early as possible.
Right. Yeah, it makes sense. I mean, like Andrew started talking in that last talk about magic state distillation and the gates, implementing gates on logical qubits is going to be so complex that you're going to need to abstract it for the end user so that the API doesn't really change at all. You're just thinking in terms of the existing gate set, and under the covers, it's doing all kinds of crazy stuff. But,
exactly. Yeah. And a lot of the people that will be the ultimate users of this are not, experts in quantum, right? They're not quantum physicists. They're folks that I think we heard someone earlier, mention that they just want to be able to use their program that they're familiar with, right? And so how can I use, whatever computational chemistry package of choice is, right? Gaussian or whatever. And then just have it interface with the quantum computer. And even, thinking about workloads and how you divvy up across HPC and quantum and where you introduce each of these things. You don't necessarily as a user want to be thinking about that. You just want that to be automatic.
Right. The one thing another thing that Martin said actually, which I've been thinking about ever since that conversation, was that he was saying that he thinks that quantum information science, some amount of it is becoming sort of a prerequisite for anybody in the physical sciences.
Interesting.
You're going to need to, that's going to be almost the assembly language of physical sciences in a way. It's like everything is going to be relying on quantum computing in some way, shape, or form in that sort of toolkit kind of way that you described. And therefore, you're going to have some kind of familiarity of thinking of problems in those terms. Do you think that's true, or do you think we do get to that abstraction where you're just a chemist and you're using Gaussian or whatever you're familiar with, and it's quantum under the covers?
It's a really good question, because I think if you're thinking about it from a university standpoint or an education standpoint, you're thinking about okay, what skills does the future workforce need? And I think that a lot of the richness of what we can do with quantum and what we can do in quantum computational science is at the intersections of different fields. So I've kind of just, from talking to folks, I've seen a couple of different approaches to that. Some have full-blown quantum programs that they're building out with core curriculum that is, just based on quantum information science and beyond. And then some programs are sort of thinking about it more of how do I have something that is along the lines of a certification program where maybe you are a chemist, but then you have this additional quantum certification on top of it.
Yeah. In fact, University of Washington has a quantum certification program for one. Yeah.
Right. Yeah, exactly. Yeah. And so how you design that is that's an interesting question. Obviously, I'm not in the university, so I can't answer that or project out.
There's probably more than one answer too.
I bet there is. Yeah. Not a one size fits all kind of thing, because the students are going to have their own kind of slants on that. Yeah. But do I think, I think that in these early days, especially, I think you're always going to need some of that. I think that people in the classical realm have gone very, I've known folks that are computational chemists that don't know how to code, right?
Right.
And that's not like it's just that they have the software.
Yeah, right.
They don't need to know.
Right.
And so maybe, if we just like project out,
right.
then that's maybe the future
Right.
as well. But I think in the early days, you're going to have to have some kind of understanding that covers a couple of different bases.
Abstraction doesn't come overnight.
Yeah, I like that. Abstraction doesn't come overnight. Yeah, it's totally true.
Yeah.
Yep.
Yeah, that's interesting. And so, again, sort of coming back to RPI, there's now IBM System 1 in the building just behind us there. What do you think the university or like the academic world has to benefit from an on-premise device? What do you think they're going to, what are you excited about seeing coming out of the RPI faculty and student body?
Yeah. Well, I think like one of the things that it definitely does is it inspires the imagination of like, what can you do? What can you actually try with your own two hands? And having something like physically present, there's a lot of motivation, I think, to do that. Because you don't have to wait in a queue.
Right. Yeah.
You just hop on. You can use it as long as you want. Maybe not forever,
and
but
the freedom are definitely
exactly
not to be undervalued.
Exactly. And there's sort of like some added additional like things that I think will be very interesting to see. Having it be co-located with an actual HPC like center will be very interesting.
Yeah.
So there's just, I think, a lot of different potential avenues to explore. The other thing is too, like, they're the first university to have a quantum, computer on site like this. And it's, I've been chatting with people and I've heard a little bit of like anecdotal like stories from folks saying like, oh, yeah, like we knew of, the student who told us that they turned down other schools to come here.
It's a recruiting tool.
It's a huge recruiting tool. Yeah, because, the students are really, I think most universities, even if they don't have a quantum computer on site, in fact, they won't yet anyway, have like...
Is there an 800 number they can call?
Yeah.
Order one?
Yes. Just call us up.
1-800 qubits.
Yeah, there you go. But yeah, I think that they... That's funny. I think that they have, student clubs, though, that like a lot of them very large student clubs.
Yeah.
And so you have to take that as an indicator. If I'm someone, at a university that like there's a lot of interest, that there's going to be a lot of interest in using something and having access to something that they wouldn't otherwise.
Yeah.
So I do think it's a huge recruiting tool, and it also will serve as an educational aid in those kind of courses that we were talking about, or certification programs or whatever, because you can literally use it how you want.
Yeah. Well, and in particular, you mentioned the integration or co-location with an existing HPC center. Do you think, that's really interesting and exciting to me, because I wonder, are there scenarios that you can imagine where there may be some, role that the quantum computer can play in otherwise a classical solution for chemistry simulation or something, and it's acting as an accelerator for one specific, subcomponent of the overall solution that you can do because you're connected to the same InfiniBand or some kind of high bandwidth interconnect.
Right. Yeah, I think that's the idea. And then you like avoid any latency or anything like that, issues that would come up. So you could potentially like explore that a little bit easier with higher fidelity. And start looking at like pieces of the puzzle. And again, it goes back to that sort of like workflow and how do you divvy it up and like what do you want to do where, and which of the different processes are better to do on the quantum device versus, on a GPU or a CPU or what have you.
Yeah, going back to Martin again, he actually did a variational pre-processing step classically before he actually loaded the circuit up on the machine. So it feels like sort of what you were saying, like there isn't a one size fits all. We don't really know what the right approach is for any particular experiment. So having the freedom to use the classical and the quantum in any number of different configurations might be sort of
totally
opening new doors, so to speak.
Yep. I mean, in a lot of the chemistry research we've done sort of like a classical pre-step as well, where you do like you try to basically minimize and reduce the amount of information that you have to put on the quantum computer, and options are usually classical for that. So like you might use DFT, for example, to down select for the orbitals that's really important for a chemistry problem. Then you can try the chemistry part on the quantum computer to get the ground state energy or what have you. So I think having that capability, I think, will be really interesting, open up new doors. And I think for many will serve as a starting point too, because they're again, the barrier to entry is probably a bit lower.
Yeah, absolutely. Yeah, you've done a ton of really interesting projects. You just mentioned, sort of in the projects you've done for customers and just internally at IBM. Are there any projects you've done in the past that you're sort of waiting to revisit, like with like either 127 or like, is there something sort of this? As soon as we have this capability, I want to go back and improve on that result.
Yeah, I think we've done some like small molecule examples of like certain. I think like the one that I really loved was the sulfonium study that we did, which is like that we did with JSR.
Right.
So it was basically trying to mimic a photoacid generator for photoresists, right? So we did sulfonium, which is just H3S plus. There was a lot of like algorithmic challenges that came with that, because you have like a positively charged molecule. You're trying to look at a dissociation where now you have radicals involved potentially. And so there was a lot, and you want to look at energy levels and excited states, which are a little bit more complex than just ground states to look at. Right. So like all of those things taken together made it, like we had to figure all this out, figure out the error mitigation method. So it was a research project in and of itself. However, it would be even better if, we could actually get to the system that is of industrial interest, to JSR. So something where now you don't have the protons, but you're looking at phenyl rings. So you have 6 carbon atoms and 5 hydrogens. It's a lot bigger.
Right. Okay.
There's different kind of chemistry because of that. In fact, the chemistry that's, they're targeting usually has to do with the aromatic nature of those rings. And so, yes, let's get to that point, right? Like, so how do, once we have these ways to divvy up the circuit and really kind of break it down, maybe we can start tackling things of that size, which would be amazing.
Yeah.
And
you're talking about circuit knitting and entanglement forging, right? Techniques to sort of decompose the problem.
Yeah, like entanglement forging is a really good example of that. And so, how can you use that? How can you use embedding methods potentially? Those are all the kinds of tools that are in that toolkit: circuit knitting, embedding, and that type of thing. And I think that, again, it's not a one size fits all. You do have to do like some trial and error. Like, does it actually help? It might not.
Right.
In certain examples too.
But I guess all of those experiments, like that's where you're going to extract those principles. You're going to end up building abstractions for the end user who doesn't have incredible depth in QIS in order to use these things. Yeah.
You learn something every time. And so over time, like as you build up a body of these, then you can make some generalities about what needs to be done and what kind of things are helpful to do in certain instances, and then potentially automate that. Right.
And has circuit knitting been used in any published research that you guys have done at this point? Or,
yes.
I know it's been experimentally done, but is it a real technique that you guys are using?
Yes. Cool. So we recently applied it. We did a study with Boeing, and we used basically entanglement forging techniques there. I would actually say in most of our current chemistry research, there's something like that.
Cool.
It doesn't work for everything. Again, that's my caveat. But most of the time, we're starting to, when we start from ground zero, we'll see if entanglement forging helps.
And sorry, I think I said circuit knitting. So you're saying mostly you're using entanglement forging at this point. And just describe at some level like how that works.
So entanglement forging is basically, it's based off of spin pair coupling. So essentially like spin up, spin down, you can separate the two calculations out. So then you half the number of qubits that you need.
Okay.
So essentially, like if you had a 10 qubit problem, you could just use 5 qubits, and you run circuits simultaneously, and then use a post-processing method to sort of knit the
So
what
it's
you
a
got out
classical
back together.
post-processing.
Classical processing. And so that's the trade-off. I think
Right.
you've probably heard Jay mention it earlier in his talk today, right? Like, is that there is some overhead affiliated with that piece of it.
Right.
But it does allow you to do kind of larger systems or systems that would be out of reach by kind of cleverly, breaking down the method. And again, it doesn't work for everything. You need to have, weakly entangled spins. So like we used, the first example of it was on the water molecule because it was like a poster child, if you will, for that.
Yeah.
And then again, it's like you always, when we start with chemistry examples, one of the first things we do is we evaluate like, okay, is this something we could use for this? Like,
Right.
does the molecule kind of fit the, check the boxes for what you could use entanglement forging for?
Right.
So, but definitely like a very helpful technique, and I think very useful for looking at some of the more challenging problems that we see like industrially and things
well, and
like
I guess, I mean, there's always going to be some amount of classical overhead, even like state preparation and error correction is going to introduce some kind of classical overhead. So, and as you said, it's not always raw performance, it's also fidelity. Like if you get a higher accuracy prediction, then that's going to help you more than necessarily just getting, something faster but still inaccurate.
Yeah. Well, that's like when I talk to, chemists and computational chemists, that's like really at the end of the day what they care about is that, accuracy level. So they'll be the first ones to tell you that a lot of these approximate methods that we've been talking about get you very, very close to the exact value. And so there's a certain kind of trade-off there. It's like if it's good enough, then why would you, address it as a challenge, right? So I think that it's in some cases much harder to get those accurate results. And that's where, like, if there is something that quantum brings there, they would be very excited about. So like transition metals is like the perfect example because they have the highly entangled d electrons. So that's a really good, I think, again, challenge to start looking at with quantum.
And any guess as to what sort of quantum volume you need to be able to start looking at transition metals?
Oh, well, I mean, I think it's going to come, well, I don't know is the answer.
I mean, that's the quantum answer. So.
That's the quantum answer. It's going to depend on the development of all these different kind of tools and methods, as well as, just having everything kind of the stage set for it. But I will say that, a lot of the techniques that we've been developing out, I think, should apply to those harder examples in chemistry that we just haven't been able to tackle yet.
Yeah. Awesome. That's awesome. That's great. I mean, it really does feel like, as you said, there's no one size fits all, and but at the same time, you're developing this broad set of tools that are incrementally progressing the field, and like, we are getting closer to this stuff actually being super, super useful.
Yeah. And for things that you could never be able to do classically.
Right.
Ever.
Yeah.
So
amazing.
Anyway.
Excellent. Thank you so much for joining us.
Thank you, Sebastian. What a great conversation.
Yeah, awesome. Excellent. Thank you.
All right.
Okay, that's it for this episode of The New Quantum Era, a podcast by Sebastian Hassinger and Kevin Roney. Our cool theme music was composed and played by Omar Costa Hamido. Production work is done by our wonderful team over at Podfi. If you are at all like us and enjoy this rich, deep, and interesting topic, please subscribe to our podcast on whichever platform you may stream from. And even consider, if you like what you've heard today, reviewing us on iTunes and or mentioning us on your preferred social media platforms. We're just trying to get the word out on this fascinating topic and would really appreciate your help spreading the word and building community. Thank you so much for your time.